So in this video, I'm going to go over a new concept that's shell method. And if you're watching this, if you have not done disk method or washer method yet, I highly recommend you learn those first. I have those on my playlist for this Cal2 playlist. Highly recommend you watch those first and then watch this video. So anyways, we're going to region bound by those constraints, but right now I'm going to show you basically the formula right here that we're using for shell method is volume is equal to 2 pi our bounds r of x times the h of x times dx. So basically our r of x is the radius, h of x is the height. So the idea behind a shell method is that we're given a disk that's being revolved. So for example, about the y-axis, we have a disk right here which is represented by the green disk right there. We have our x limits, and the radius is the distance between the disk to the axis of revolution. So that's our r of x. So I want you to know that r of x is the distance between the axis of revolution and the disk. And h of x is the function that's given to us, and it's the height between, it's the height of the disk basically. So r of x is the height of this green disk right here. And our r of x is just the distance between the axis of revolution and the disk. And we can do this with respect to y as well. So we see that it's the same concept. The distance between the disk and the axis of revolution is r of y, and the length of the r of y is the height. So I want you to familiarize yourself with the radii is perpendicular to the axis of revolution and the height is parallel with the axis of revolution. So as mentioned in the instructional to this video, so key takeaways from this graph is that when it revolves about the y-axis, we use x terms. So our h of x can be, when we're given two different functions, it can be f of x minus g of x. When it revolves about the x-axis, we use y terms, and the h of y is equal to f of y minus g of y. So let's go a little deeper into the height when we're given two functions. So with respect to x, we're given these constraints. We know our x of L and x of R. So one thing I want you to notice is that the height of the disk can now be defined as two functions, f of x minus g of x, f of x being the upper function, g of x being the lower function. Our radii is still the same. The radius is still the distance between the disk to the axis of revolution. In this case, it's revolving about the y-axis, so it's r of x. And now with respect to y, it's the same concept. So we have our lower y limit and we have our upper y limit. And it revolves about the x-axis. Our h of y is the distance between these two functions of the disk. Because notice the disk does not start, the height of the disk does not start at any particular point, so we have two functions defining the height of the disk. So the difference between the two of them is our h of y. Our r of y is simply the distance between the axis of revolution and the disk. So again, about the y-axis, we use x terms, and h of x is equal to f of x minus g of x. And about the x-axis, we use y terms, and h of y is equal to fy minus gy. So now for step one, we're going to sketch this out. So we're given the region bounded from x equals 0, x equals y squared, y is equal to 0, y is equal to 2. It goes about the x-axis. So we're going to go ahead and sketch all this out. So we know our y limits are from 0 to 2. We know that the disk looks something like this. We're given our r of y and we're given our h of y. Why? Because this revolves about the x-axis, so we're going to use y terms. So it's unlike disk and washer method. Revolves in disk and washer method, it's opposite. So that's the tricky, trivial part about shell method. It's different. It's opposite, basically. It's not different, it's opposite. So when it revolves about the x-axis and you have y limits, you use the y terms. So when it revolves about the x, use y. When it revolves about y, use x. In this case, it revolves about the x-axis, so let's use r of y and h of y. H of y is the function that's given to us of y squared. The difference, the height of that, the disk is from this point right here to the axis. So it's just y squared, and the r of y is the distance between the axis of revolution to the disk. So now we're going to identify the variables of integration. So one thing I will highly recommend you do is copy this chart down right here. When to use f of x and when to use r of x hx and when to use r of y hy. So we use r of x h of x whenever it revolves about the y-axis or any axis parallel to the y-axis. Example given when it revolves about x equals 1. So when your function revolves about y, use x terms. When you're given x limits, use x terms. So find a way to make this rememberable. Or just copy the chart and you do a couple problems and then it becomes easy to remember. So basically, when to use r of y, when it revolves about x. When to use r of x and h of x when it revolves about the y-axis or anything parallel with it. So now we're going to redraw that sketch right here. So we're going to use r of y and h of y because this revolves about the x-axis. So what is h of y? Well, h of y is what's given to us, so I'll include our y squared, but r of y is actually just y. As stated right here, r of y is just equal to y because it's just a distance from the axis of revolution to the disk. So in this case, the axis of revolution is the x-axis, so it's just y. If it was x equals 1, then it would be y minus 1. That would be our r of y. So in this case, our r of y is equal to y. Our h of y is equal to x. And our h of y, x, is equal to y squared. So now what we're going to do in step 3 is we're going to find the limits of integration. Well, from the graph, from the sketch that we had, we know the limits of integration were already given to us. And by the way, these are the limit variables I use. This is just a naming convention. Yt means top limit y, yb means bottom limit y, xr means right limit x, xl means left limit x. So that's the naming convention I use. You can use whatever naming convention you want to use, does not matter. I use these because it helps me know when I have y limits, when I have x limits, and the subscripts help me know exactly whether I'm taking an upper bound or a lower bound. So now, the limits that were given to us was the bottom y was equal to 0, and the top y was equal to 2. Those are bounds of integration. So now, we're going to set up the integral. So the integral formula is the volume is equal to 2 pi y bottom to y top, r of y, h of y, dy. And so now that we have everything, we're going to plug it in. Recall our r of y was equal to y, and our h of y is equal to y squared. So from here on out, what we're going to do is we're going to plug everything into the integral. So the volume is equal to 2 pi from 0 to 2 of r of y, which is y, h of y, which is y squared, times dy. And in step 5, we're going to integrate this function. So now the integral is very simple because we combine this, we get the volume of 2 pi of 0 to 2 of y cubed. That's in essence y to the 1 power times y squared is y cubed times dy. So now we're going to integrate this, plug in the limits and solve. So when we integrate y cubed, we get y to the 4th over 4 times the constant of 2 pi bounded from 0 to 2. We're going to simplify this a step further. because we know we can simplify 2 over 4 to pi over 2. And then y to the 4th power, bounded from 0 to 2. And we can simplify this a step further because we're going to plug in the limits. So pi over 2 we can simplify of 2 to the 4th power minus 0 to the 4th power. And we know the last term is going to 0 out. And we're left with 2 to the 4th power is 16 over 2, which is equal to 8 pi. So that was the shell method. So I think the key step is knowing which axis, what your terms are going to be. That chart that I set up right there, that's the key step. Understanding that chart, you'll be able to do any shell method problem. So in this example, we're going to go over how to do shell method applying a region bounded by the first quadrant, y equals 0, y is equal to x squared minus x to the 4th, and it revolves about the y-axis. So the first thing we're going to do is we're going to sketch this out. So when we sketch it out, it looks something like this. We have a line of x squared minus x to the 4th, looks like that. And again, h of x is the height of the disk, and r of x is the distance between the disk and the axis of revolution. And why I'm using x and not y terms is because since it revolves about the y-axis, we use x terms, as noted by shell method. So our r of x is x, and the h of x is the function given to us. On step 2, what we're going to do is we're going to identify the variables of integration. And to do this, I think we need to follow this chart right here. So, and the sketch that we drew, we're going to go ahead and follow it and identify that since it revolves about the y-axis, as stated right here where my mouse is, we use x terms. We use r of x and we use h of x. R of x is the distance between the disk to the axis of revolution. H of x is the height of that disk. So our r of x is simply just equal to x. So since it revolves about the x-axis, the height and radius should be in terms of x. Or since it revolves about the y-axis, that's supposed to say y. So h of x is equal to x squared minus x to the 4th power. R of x is equal to x. And this right here is supposed to say y. So since it revolves about the y-axis, height and radius need to be in terms of x. So just know that. Since it revolves about the y-axis, height and radius should be in terms of x. So that's our h of x is the function given to us right here. And r of x is the distance from the disk to the axis of revolution. We're going to call it x because it's right on the axis of revolution. Now what we're going to do for step 3 is we're going to find the limits of integration. So note that in this problem, the limits of integration were not explicitly given, so we do have to find them. So again, this is a naming convention I use for limits of integration. We know h of x was equal to, we're going to set h of x equal to 0 to find our limits of integration. So we know that x squared, we're going to add x to the 4th power to both sides, so we know x squared is equal to x to the 4th. Thus, we know that we can divide it. We can split up x to the 4th as x squared times x squared, and we can divide both sides by x squared. When we do that, these terms will cancel out, and we're left with x squared is equal to 1. Thus, meaning that x is equal to plus or minus the square root of 1, which is plus or minus 1, basically. And since this is in the first quadrant, we're going to omit the -1 boundary, and we're only going to focus on the positive one because the region is bounded explicitly where my mouse is right here, the first quadrant. So we know the left limit x is equal to 0 and not -1 because it's in the first quadrant, and the right limit x is equal to 1. So with that information, we're going to set up the integral. So we know the formula for the integral with respect to x terms is volume is equal to 2 pi, bounded from xl to xr of r of x, h of x, and d of x. And we know our r of x is equal to x, and we know our h of x is equal to x squared minus x to the fourth power. So our volume is equal to 2 pi 0 to 1 of x times x squared minus 4 times dx. And again, our r of x and our h of x are these terms right here. So our r of x goes to x, and our h of x is x squared minus x to the fourth power. So that's how I set up the integral, by plugging in r of x and h of x. So now, what we're going to do is we're going to do step 5, which we're going to integrate this function. So in doing so, we know the volume is equal to 2 pi bounded from 0 to 1. And what we're going to do is we're going to distribute that x of r of x into h of x. So x times x squared is x cubed minus x to the fifth power times dx. And when we integrate this, the integral is very easy to compute. So we know x cubed integrated is x to the fourth over 4 minus x to the 6 over 6 bounded from 0 to 1. Now we have the integral set up, we're going to go ahead and quickly copy down what the integral was that we computed was 2 pi x to the fourth divided by 4 minus x to the 6 divided by 6 bounded from 0 to 1. And now we're going to plug in the limits and solve this. So the first approach I'm going to take in plugging in is x to the fourth over 4 minus x to the 6 over 6 bounded from 0 to 1. I'm going to find a common denominator by finding the least common multiple of 6 and 4, which I got. Well, I decided to use 24, but you could also use 12. So that's what I did. I used 24. So I multiplied the first fraction by 6 over 6, the second fraction by 4 over 4. And I got 2 pi of 6x to the fourth divided by 24 minus 4x to the 6th divided by 24, bounded from 0 to 1. And the volume is equal to 2 pi over 24. And then 6x to the fourth minus 4x to the 6th power, bounded from 0 to 1. So now what I'm going to do is I'm going to simplify and plug in. So I know the volume is equal to pi over 12 of 6x to the fourth minus 4x to the 6th bounded from 0 to 1. So now when I plug in, I get 6 to the 1, 6 times 1 to the fourth power minus 4 times 1 to the 6th power minus 6 times 0 to the fourth power minus 4 times 0 to the 6th power. And I know those last two terms were 0 out. And I'm left with the volume is equal to pi over 12, and then 6 times 1 to the fourth power, 1 to the fourth power is 1 times 6, so it's 6 minus 4, and of course minus 0, which that term zeroes out. So we're left with the volume is equal to pi over 12 times 2, which is equal to pi over 6. So that's the answer to this shell method problem. So basically the key here was that it was revolving about the y-axis. So we had to use x terms, but we were given a function in terms of x, so we had to solve for it. Anyways, I hope this video was helpful. Thank you for watching. If it was, feel free to like, share, subscribe, leave a comment, leave feedback. Thank you.